So next up, we've got Stefanie Molin. Stefanie works at Bloomberg in New York. She's a core contributor to NumPy doc, and she's written an excellent book on pandas, and she's here to warn us about summary statistics. So with that, I'll hand over to you, Stefanie.
Thank you. OK, so today I'm going to talk to you about a project of mine called Data Morph and why you have to be very careful when using summary statistics. So we kind of covered this a little bit. I'm a full stack engineer at Bloomberg in New York City. And I'm also the author of this giant book on pandas here. I'm giving away this copy, so come see me afterwards so I don't have to put it back in my suitcase. So summary statistics aren't enough. If we look at these three data sets, I'm sure we would all agree that they are very different visually. But if we look at the summary statistics of the mean, standard deviation, and correlation, they all have the exact same summary statistics. So the same mean in x and y, the same standard deviation in x and y, and the same Pearson correlation coefficient. So what we actually need to be able to summarize or look at the difference between these data sets at a numeric level is to use what are called moments to describe the shape of that distribution. So you can see at the bottom we have the second moment is the same, right? So the second moment is going to be the variance. So we saw standard deviation was the same, so variance is the same. But when we go to the third moment, which is the skewness of the distribution, we now can see differences between x and y, between all these data sets at a numeric level. If I then add the marginal distributions, which are these histograms for x and y, again, looks very different visually. And now I've replaced the third moment with skewness, and the fourth moment down here is a new thing. We have the kurtosis. So the skewness is a measure of the asymmetry in the distribution. So for example, something like this, you can see has a very high skew in y. And then the kurtosis is a measure of the weight in the tails being these at the end. So again, once we move all the way to these statistics, these moments, we're now starting to see differences in these data sets. But now we've lost that context of how x and y move together, right? And so this is what's typically we would use the correlation coefficient. Now, in this case, or in most cases, the default when you ask for the correlation coefficient is you get the Pearson correlation coefficient, which is a measure of linear correlation. So if you're not sure what your data looks like, then you have to be very careful drawing any conclusions from that number. So here, this basically says that there's no correlation, so it's not a huge deal. But if we look at something like Anscombe's quartet, which is, I'm sure many of you have seen this data set before. It's very commonly used in statistics courses from 1973. Again, they all have the same 5 summary statistics across these 4 data sets. But the difference here is that this correlation indicates a strong linear correlation in all of these cases. However, only 1 and 3 are actually linear. Right? So if we had not looked at these visuals and just looked at these summary statistics, we would be drawing incorrect conclusions for data set 2 and 4. So it's very clear that visualization is essential to any data analysis. And I wanted to walk you through the results of a 2020 paper called A Hypothesis is a Liability. And the researchers here argue that simply approaching a data set with a hypothesis in mind may limit the thoroughness to which you actually explore that data. So in their experiment, they took students in a statistical data analysis course, and they split them into 2 groups. One group was told to just explore the data set and report back on what they found. And the other group was given a set of 3 hypotheses, which I have up on the screen, and they were told to test those hypotheses and report back. Now, if you look at them, they're dealing with summary statistics that we were discussing before. This was the data. So the students who were given the hypotheses to test were 5 times less likely to realize that the data set was fake and shaped like a gorilla. So how do we encourage students and practitioners alike to be more thorough in their analysis, to not skip that step of visualizing their data? So one way I would argue is by creating more memorable teaching aids. So in 2017, researchers at Autodesk made what's called the Datasaurus Dozen. So building on top of Anscombe's quartet, they this time took a dinosaur which is called the datasaurus, and they used a technique called simulated annealing to convert it into the 12 shapes seen below. Again, sharing all the same 5 summary statistics that we saw before. So already this leaves a bigger impression than Anscombe's quartet, right? The dinosaur is a very shocking visual. And the other thing that they did was added animation. So now you can appreciate that it's not just that dinosaur and the circle that share the summary statistics, but it's every different combination of points that we get on the way from turning one into the other that also has that same set of summary statistics. Right? So there's infinite number of things that would apply to that set of summary statistics. And this has now led to a new problem. What is so special about that datasaurus? If you look at posts that people put online, they're marveling at the fact that this special data set was constructed in a way that makes this possible. And that is simply not the case. This can be done with any data set. And so this was part of the reason why I set about building Data Morph. Because people were incorrectly attributing that to a property of the way those points were constructed, it was clear that the goal of making a memorable teaching aid that people would not fall into that fallacy over and over again was not doing the trick. People were now attributing, well, my data set's not a dinosaur, so I'm not going to have that problem. I don't need to visualize it. And the other thing is that repetition is key. So Data Morph is, as I mentioned, a tool that I built, and it extends the research from Autodesk. But I addressed several of the limitations of those previous methods I discussed. So first off, it's an installable Python package, so you don't have to hack at the researcher's code base. You get those animated results automatically when you use it. You can use your own data sets, like via CSV of points, or you can use additional built-in data sets, so it's not just the dinosaur. And then you can also experiment with various target shapes, and I'll show you examples of these later on. So this now means that the number of examples that can be created to illustrate this process is now no longer frozen by Anscombe's quartet and what the research of that paper provides, dinosaur to everything else. So here's Data Morph. And I'm converting the Python logo into the shape of a heart, and again, preserving the summary statistics the whole time. So to create that, first, you can install the Data Morph package from either PyPI or Conda Forge, and then that provides an entry point called Data Morph, which then you can call on the command line, saying that you want to start, in this case, from the Python logo, and convert it into a heart. So under the hood, this is a high level of what's going on, and I want to walk through each of those steps. So the first thing that we have to do is select our starting data set. So this is done with the data loader class in Data Morph. And so this class has a load data set method where you provide either the name of the built-in you're using or a path to a CSV of points that you want to use. So a data set is not just a set of points. This was something that I added on top of the initial research. There was no abstraction of what it means to be the collection of points. And this is part of why Data Morph works for arbitrary data sets. So the Data Morph data set is the points, which you can see here forming the Python logo, plus these automatically calculated bounds, which you can see here. So the innermost set of bounds, this one here, is the bounding box that the smallest bounding box that captures all the points of the data. The middle one are the morph bounds. So this tells the algorithm how far it's allowed to push the points away from the starting shape. And then the outermost one are the plot bounds, and this tells where the frames should be selected for actually plotting for the animations. And so these bounds can then be used by the shapes, which I'll discuss next, to determine where they should be in two-dimensional space. So this means that it's no longer hard-coded like it was in the research. So basically the research was, if you're using a dinosaur and you want to turn it into a circle, the circle is this exact dimension in this exact spot in 2D space. That does not scale. You cannot use that for anything arbitrary. You're stuck with hard-coded values. So the bounds allow you to define heuristics that you can then apply to arbitrary data sets. So if you download, or sorry, if you install Data Morph right now, these are the data sets that are built in as available. And I also have, I think, 3 more coming in the next release that were contributed by people at sprints I did at conferences earlier this year. So once that data set is defined, then we can create the shape. So the shape doesn't exist without the data set. So in Data Morph, this is done with the shape factory. It's then initialized with the data set. And then it has a generate shape method where you can specify which of the built-in shapes you want to use. So in this case, the heart. So a shape, as I mentioned before, doesn't exist without the data set. So rather than having, again, those hard-coded values of if you're starting with some data set and you want to use some target shape, then it has to be in this exact spot. You'll notice that in the top row, I'm using the Python logo data set, and in the bottom row, I'm using the music data set. They are different aspect ratios, right? You can see that the Python logo is the same in X and Y, and the music data set is taller than it is wide. So in both cases, the shapes are able to place themselves on it, and again, notice the axes are also completely different. So without having to hard code anything, the shapes use the bounds information on the data set to determine where to place themselves, and then so that's the translation in X and Y, and then also how to scale themselves. Should they be scaled up? Should they be scaled down? Depending on the scale of the data itself. So again, if you had installed Data Morph right now, these would be the shapes that you would have available to you. There are more also coming from some sprints earlier this year, including a spade and a club. So we have the full set of card suits in addition to these 2. And hopefully, if you come to the sprint, which I'm planning to do on Monday, then you can help me add a few more to Data Morph as well. So as I mentioned before in the initial research, shapes didn't exist. It was just a giant if-else, and basically a lot of repetitive code that we're effectively creating some stand-in for a shape at each iteration. And when you think about it, the algorithm is just working on distances. So it doesn't need to know what a star is, what a heart is, right? It just needs to know that given a point that I want to move, what is the distance of this point to the target shape that we're trying to define? And so I made a layer of abstraction here, which is the shape hierarchy. So a shape only has to do 2 things at a high level. It has to have a plot method so it can be visualized. And then it has to have that distance metric. So given a point, it tells you how far away that point is from it. And then after that, the 2 main classes are the line collection and the point collection. So a line collection is a collection of different lines, and the distance is then just the minimum to the distance to any of the lines. The point collection is likewise a collection of points. The distance is the minimum to any of the points. So once you have those defined, then any shape that you want to add that is a set of lines or a set of points doesn't need to be, you don't need to figure out how to calculate the distance. It's already done for you. So at a contribution level, all you have to figure out is, given some data set, some set of bounds, how do I draw this shape in 2-dimensional space based on that data in such a way that it works for a variety of data sets? So kind of defining heuristics. So once the data set and the shape are then created, then the actual morphing algorithm can happen. And this is done with the Data Morpher class. And you'll also notice here that you can define how many decimal places you want the statistics to be held the same to. So in this case, I'm using 2. So the way this algorithm works, and this is largely untouched from the initial research, is using a technique called simulated annealing. So here you can see I've overlaid on the right side the target that we're moving towards, the heart. So at each iteration, a point is selected at random, and that's when it is highlighted in blue. And then it's going to be moved a small random amount to a new location, and that's when it glows red. The catch is that it won't ever move a point to a location that then makes the summary statistics change. So it's constrained in that way. However, it is allowed to move the points away from the heart shape, so technically in the wrong direction. And this is done because this allows it to avoid falling into a local optima, where the algorithm might get stuck. So the likelihood that this happens is governed by the temperature of the process. And as you can see, it decays over the full number of iterations that you run the algorithm for. So in the case of 10,000, at the end, you effectively are doing this close to 0% of the time. And the same thing if you went all the way to 100,000 iterations. So one thing I added on top of that is applying that logic to how fast the points are moving. So I decrease the amount that they move over time. And this gives the visual effect of the points like scurrying away at the beginning and then slowly settling in as they get towards the shape at the end. And again, this uses a very similar process to the temperature, but the exception is that we cannot let this go to 0 because then effectively nothing would happen and you're wasting processing time with those iterations. So this decays to a smaller number. Okay, so I want to talk about some limitations of all this and some areas for future work. So the first thing is what I call bald spots. So probably when I introduced this in the beginning, you were picturing something like on the left, where the heart looks very nice, perfectly filled. But what ends up happening is something more on this side. So you can see, for example, here, where it's faded out, and hopefully, yeah. So no points ended up in this bit or on this curve here. But we have tons of points that clumped all together in the bottom. Right? So right now, there's no penalization factor for points moving in the same spot. There's no like repulsion force. So they just went to a spot that was close. When you think about it, this was like the arm of the dinosaur. So they all ended up there. So something I'd like to look into in the future was how do we encourage the points to fill out the shape better. Next thing is the direction of the morphing. So we start from a data set, and then we convert into a shape. And those I described in the beginning before because they are different entities. And technically, you can do shape to data set if you just play the animation in reverse, right? But going from data set to data set, for example, if I wanted to turn the dinosaur into the Python logo, how do I scale one over the other? What is the best distance metric to use? How do I solve the bald spot problem so I don't have a T-Rex with no head or something? And then the other thing is shape to shape. So the shapes are defined based on the data sets. If there's no data set there, then which shape is the one that we start from? How do they go to, like, in between each other? So that's another thing. Another consideration is the speed. So the algorithm is very iterative. You take a point, you try to move it to a spot that will preserve the summary statistics. You might have to do that a few times to find one that actually does preserve the summary statistics, and then you run the check to see, well, am I allowed to make a wrong move if this was a wrong move, right? So you might end up having to run multiple iterations before you effectively actually move your point. So, and then each little move, you're not affecting the summary statistics to a noticeable amount because we're freezing it to, like, say, 2 decimal places, but you are changing it many decimal places further down, right? So each change, you do have to observe the effect of it. So thinking about how to possibly vectorize that is a bit challenging. The next thing is that the scale of the data affects the morphing time. So if we look here at the data of the dinosaur in the middle, this is the size that we've been looking at before. And this takes about 50,000 iterations to convert satisfactorily to a circle. So if we scale this down to half size, this takes about 25,000 iterations, and up to double size, about 78,000 iterations. And this is because we're moving small amounts at each iteration. Now, if you try to increase this number, it ends up the algorithm gets stuck. So it's not just a matter of flipping that. And then this also leads to the next problem related to that, which is the convergence, right? So I mentioned running a certain number of iterations. Right now, that is how you define that you're going to run this algorithm. You say, I want to run for 50,000 iterations. Then you look at the results, and you might say, oh, geez, I needed another 25,000. Let me rerun again. And you have to start over. On the flip side, you might realize that, oh, I definitely didn't need 50,000. And now I want to run the animation again, or create it again, because I want to not have the points just dancing around at the end. I want to have a more seamless transition. And so you have to run it again. So what I'd like to do is move towards having an idea of a convergence criteria. So you could say, I want to run for 50,000 iterations, but it might stop earlier if it sees that it's gotten close enough to the shape. Okay, so I want to talk about now the lessons I learned converting this research into a Python package and some of the challenges I faced along the way. So repeating research is hard. I started with the Autodesk researchers' code, which they had published a version that they had cleaned up a little bit. And I wanted to just recreate what they had done. So converting the data source into a circle, just so I can see what the magic numbers that they were using actually meant. So at this point, there were limited to no code documentation anywhere. And as I mentioned before, they had carved out pieces of the code base, and so that's something that they would present publicly. And that meant that then there were parts of the code that were not used at all. And you would see a function, you wouldn't know what it is, it wasn't documented, and it wasn't used anywhere. It's hard to tell if it actually added something or not. And then you had generic variable names everywhere, which added to the problem of no documentation. So it took me about 4 hours just to reverse engineer kind of what they had done, like which packages did I need to install, how did I get this working on my machine. And then I wanted to get this to work for a panda-shaped data set. So I wanted to convert, initially I wanted to convert the panda into the dinosaur, and I quickly realized that that was definitely a later problem. So I backed up and tried to figure out how I could convert the panda into the circle, just so swapping out the dinosaur. So I created a panda data shape, and then I messed around with it so it had similar summary statistics to the dinosaur, so I could kind of figure out what those magic numbers I mentioned before were. Again, the limited to no code documentation did make this challenging, that partial code base with things that had been chopped up and removed, and finding those hard-coded values and figuring out how were they related to data. Oh, okay, this value here must be the mean of the x, and that one must be the mean of the y. How do these relate to now swapping out that data set? So it took me almost 2 days just to get a different data set with almost the exact same summary statistics working. And then I realized that this would also be a nice teaching tool to have. So rather than just using it for myself in one of my workshops, I wanted to convert this into a package so that other people could play around with this idea themselves. And here I had way more problems. So I had to atone for all the technical debt that the researchers had accrued. So getting rid of all of those unused variables and functions and turning what was maybe 1 or 2 files of a monolithic code base into separate modules, modular code, classes, and structuring it as a proper Python package. And because they had no documentation, I wanted to make sure that I had all the documentation. So I put together a pre-commit hook for validating that the doc strings were in NumPy doc style or following the standard. And that ended up leading to me becoming a core developer of NumPy doc. I also had to figure out a lot of things that you take for granted, especially as you work in a company, right? When you have other people at your disposal to figure out what is our best practice for building the docs, where do we host them, how do we publish packages? All these things that, again, you take for granted, and especially if you've contributed to open source, usually someone else has figured it out for you. So starting from the ground and doing all this yourself, you really get an appreciation for all the work that people who create an open source package really do. So, figuring out how to build and host documentation in a way that other people could access it. How do I design a test suite from scratch that I'm happy with? I think I rewrote it at least 3 times since creating this package. And then figuring out how do you actually publish a package to PyPI? And then even more complicated, how do you publish to Conda Forge? how do you automate workflows with GitHub Actions? So all this stuff I had to figure out. And I got the first version of Data Morph published in about 2 months' time. And that was largely because I was slated to go on a podcast in 2 months from when I started this, and I really wanted to talk about it. So I really had to work very hard to get this done in time. I definitely think it would have taken more 4 or 6 months if that hadn't been the case. Okay, so a side note here about documentation, right? Even if it's well put together and there's a lot of effort got into it, you still can't completely trust it. I think that when you're new to a tool, then your gut reaction when something isn't working is always to think that, oh, I must be doing something wrong. But sometimes it is actually wrong in the docs. And so here I had 2 cases where I couldn't get something to work that I was new to, and it turned out to be things were wrong in other spots, and so I did get those fixed. So here I have some helpful resources that I consulted when I was setting this all up, talking about GitHub Actions, publishing documentation, GitHub pages, etc. And all the slides are on my website, so you can get these later. Okay, so wrapping this up, summary statistics are not enough to describe your data, and you absolutely need to visualize it no matter what you're doing. And I also encourage you not to just leave it at one plot. We saw that just adding those marginal distributions added a lot more context than just showing the scatter plot. So definitely make as many plots as you can. And be sure to try out Data Morph. So as I mentioned before, you can install from PyPI for here, or Conda Forge on this one. And here are the docs, the repo itself. And if you are a teacher, please look at these classroom activities that I've put together. So ideas that you can use Data Morph in your classroom, ranging from someone has not coded at all and they want to just see these concepts, to some more math-based things of how you design a shape and work with heuristics. And as I mentioned, I will be doing a sprint on Monday, so come join if you want to learn how to contribute to Data Morph. Here are the papers if you wanted to look into those. And thank you for your time. You can scan that code and let me know what you thought of the talk, and the links on the right if you want to follow my work. And again, I'm giving this book away, so please don't make me put it back in my suitcase. Okay, thank you.
Thanks very much, Stephanie. That was awesome. Before Kai finds someone with a question, one thing I really want to ask is, what's one of the most egregious, misleading summary statistics you've seen in the wild? Like in the wild, I found out when I moved to Perth that it actually rains more in Perth than it does in London. Anyone who's lived in both will be hopefully surprised by that. So,
I echo the thing on the weather. Like, yeah. I've done some analysis, like U.S. weather data, and like the windy city, not as windy, like the rainy city, not as rainy as other places. It's all relative. I think that's the key to it, like not just showing numbers, but contextualizing with the visuals and showing the comparison. I think like when you just say in isolation, that doesn't really mean anything. So yeah. And I would also highlight spurious correlations. If you've heard that one, the website, where they show 2 curves of completely unrelated things, and they are actually completely correlated, but there's no causation at all in that relationship. Like movies Nicolas Cage was in to drowning deaths in some place, like no relation. But it's very interesting to look at what the guy comes up with. Yep.
Thank you. Have we got any hands in the audience?
Thanks very much for the presentation. Just thinking out loud a little bit, I agree completely that sort of those summary statistics can be hugely misleading. I think of Anscombe's quartet and often think it's often sort of too abstract to have impact, but then I think of stuff like dinosaurs and pandas and Python logos, and that almost feels too absurd. Like, oh, okay, even though we can see it morphs between, it's somehow being constructed. Do you think of, and I often think about execs or non-technical managers or people like these who maybe also need to understand that we have these sorts of problems. Are there sort of like adult versions of, it's maybe the wrong way to word it, but they're more like sort of mature versions of these sorts of images that we can think about. So, stuff that looks more like the sort of corporate graphs that you'd see, or, something like that maybe has a bit more buy-in from more senior management and businesses.
I mean, I would argue that Anscombe's quartet probably is more business focused, right? Just curves and lines. You can use your data set if you want in Data Morph as well. I think it does lose the impact because people are just like, oh, it moved from some points to something and now it's back to some points. Yeah, the main focus of this is on educational tool, but I think you could try it with your data as well for the executive level, if that makes sense.
Hello? Hello? Did you get the panda working?
I did, yeah. So if you go into the documentation, so this is to get you to go to the documentation, there is, the front page is a panda converting to a star. I saved the Python logo for a Python conference.
Have we got any more questions? No? Right, well, in that case, I know you're hoping to save on suitcase space, but unfortunately, we've got a stylish and practical Pycon mug to say
This is much lighter, so I think we're good. Thank you.
Yeah, enjoy, and thank you very much.
Thank you.